So welcome to the second video of our dynamic programming lecture, and today or in this video we will talk about value iteration. So where we are right now. So actually in the last lecture we covered MDPs. We actually formally described our problem as an MDP, and we defined dynamic programming in the last video as a general framework to apply suboptimally structured problems like Bellman equation operators to actually solve our MDP. In this video, what we actually want to do is we want to estimate a value function, and then we just want to act greedily with respect to our value function. So this is actually the most simplistic idea that you can think of, and this is actually what we also did in the two simplistic examples in the previous video. So I would say at this point the easiest thing to do is just to introduce a little bit of pseudocode, talk this through, and then we can follow with an example so that you get actually the intuition about. So value iteration is one very simple algorithm that lets us get an optimal controller for a given known MDP, and actually also its convergence is guaranteed. So if you wanna dig into details on this, you can also look up in this book, and then you will probably get some performance proofs on this. So what's the general idea behind value iteration? The general idea that you loop like in an infinite loop, that you go over all your available states, and you keep track of values or state values of your states, or also state action values, but we will consider state values in here. And you have a current estimate, and based on this current estimate you calculate with the information on your MDP the state value estimate of all the successor states. So this is the basic idea that actually lets you update your state value estimations, and if you do this over and over again for your whole state space, at some point this will converge to a solution that is stable, that will not change anymore, and this is then the value, and then your value functions can actually, then you actually have all your value functions, and if you have your value function for all of your states, you can just output a deterministic policy pi, which is actually taking the argmax over the available actions. So let's maybe go through the algorithm in a few steps. So what you do is that you initialize a this is like an epsilon counter, so how much did something change with 0. But what you actually do, you do an infinite loop over your whole over your state sets, and you do this until you get an error margin that is below some threshold. So you just wanna loop until every change in your state values is below some threshold. This is the outer loop. And in the inner loop, you loop over the whole state set. And what you do is you take the current estimate of your value function of this state, and then you look at the state and look at every action that you can take in the state, and you sum up the probability of the successor states times the reward you get to this successor state, plus the discounted return of this, the discounted value of this successor state. So this is actually the iterative application of the Bellman optimality operator in here. So you wanna reset your state value to the maximum that you can get. So you take the maximum, the best action that you can take, that actually returns the largest value of the weighted value of the probability ending in some successor state S prime, plus times the reward you get transitioning to this, plus the discounted value of the successor state. And the maximum, the action that maximizes this value is actually returning you the value of your current state. And then you take the max from it, and then you assign it, and you go and you loop over all the states. If you do this, at some point you will get stable behavior. You will not change any values anymore. So you will go out of the loop, and if you have the value function calculated for all the states, you can just output a deterministic policy pi that is simply for each of the states. You just say, okay, for each of the state, I will select the action that maximizes this equation. So basically saying that if the action takes me to S prime, the weighted probability of taking me to S prime times the reward I'm getting plus the discounted value of the successor state. So the action that maximizes this is actually the action I want to take in the state in state S, because this is actually the best that I can get out of it. Maybe let's just roll out an example. I think you will also implement this during the exercises. Okay, but maybe let's take a simple example from this. I also plotted you, I also put the formula of the equation here, which is basically the optimality operator. And we will refrain to the grid world example that we also have seen before. We have a start state, we have an end state, and the positive and the negative return. What we will do in here is we will add some noise to the environment, which is something that is very common. So just imagine that it's a little bit windy in the environment. And this basically says that if you want to decide on your upwards action, like going up, there's an 80% chance that you really go up, but there's also a 10% chance that you drift to the left, or a 10% chance that you drift to the right. If you take up, in this case, there's not a chance that you go back. This is one thing. If you are at the corner in here and you select up, you will just retain in this state, so you will not move. So yes, and so there is no way to go up. And we have a discount factor of 0.9, so we will discount future rewards with a 0.9 discount factor. And there is no living reward, so basically meaning that there's neither a cost nor a reward if we transition through the environment all the way, which is basically something that's not very common in practice. What you usually want to do is that you want to add a reward of -1 for the transitioning between cells in here. Okay, so maybe let's just start it. We say our state space is just all the cells, and there is probabilities that actually let us hop between those cells. And I also put you some remarks in here. So noise is 0.2, gamma is 0.9, there's no reward for transitioning. And what we actually do in the beginning is that we initialize our value function with 0 everywhere, but we immediately say that that the value of the successor states in here is the reward that we get from there. So this is the initialization step without transitioning between any states yet. Okay, so and now if you imagine what was the original goal, so we loop over all our states and try to bootstrap or try to update our value function estimate for this step. How do we do this? So I actually put it down a little bit more in more detail for V22, for S22, which is basically this cell in here. If we want to calculate the value function update, or the value function of the state, it's basically applying this formula in here. So we want to, for each action that we might want to take, so we can take right, left, up or down. So this is the certain actions that we can take. And actually, what is the equation telling me for going right? So the equation is telling me for going right, there is an 80%. So if I select the action right, there's an 80% chance that I actually end up in here, meaning that I get no reward for transitioning between those states, but I get a discounted reward, so 0.9 of 1, this is the value of the successor state, if I end up in here. There is also a 10% chance that I end up in the same state again, so that we go left and retain in the state, and there's also a 10% chance that I go down, but this is also currently 0, so there's a 10% chance of getting no reward for the immediate step, plus a discounted discounting of the value of the next state. Maybe another example for going up. So if I'm in this state and I'm going up, there is a 80% chance of just staying in this state, so getting a value of 0. There's a 10% chance of going left, also having a value of 0. But there's also a 10% chance to actually end up in here, which basically means here I have a 10% chance of getting an immediate reward of 0 plus a discounted plus a discount of the next value, which is basically this one, which also gives me some value for taking action up. So if I break this down and I'm calculating all this through, I end up in a vector telling me I have a 0.72 value if I'm taking action right, a 0 value for taking action left, 0.09 for up, and 0.09 for down. Actually letting me end up in a maximum of 0.72, which is actually in this case taking action right, which is something which could be intuitive at this point. I also can do this for this one cell in here, which is actually very similar. So actually if I'm in this cell and I'm selecting action right, there's an 8% chance getting no reward for the immediate step plus a discount of a -1 value, which is actually something not very bad. And we also see this in the windy noise action in here, like in the previous state as well. If I'm calculating this through, I get a -0.72 for this state going right. And if I'm selecting the maximum from it, this would be, of course, for this kind of current value function estimate, going left, because if I'm going left, I will not get any negative reward because I might end up in here, or due to noise in here or in here. I can expect a value of 0 if I'm in here and take the action left, because there's, for the current state of information, nothing else that I can expect. Okay, and I can also do this for this state and for all the other states as well. So in this state it will be 0.43. Yes. Okay, and now what's really interesting is if I'm now sweeping over this, so for each of the other states it was really like boring because everything remains 0. But if I do this in the second term, actually now estimations get a little more clear, or approximating the real values a little clearer, because actually if I'm now updating this function or this value in here, I will not consider a 0 return or 0 state value of this one, still a 0 value of this one, but there is now something different in here, which actually lets me calculate a value that's more realistic than in the beginning. So starting from here, I would then take the 0.72 for my calculation in here. So you look this. So if I'm in the state now and I'm selecting the up action in the previous iteration, I assumed the state value to be 0, but now the state value is assumed to be 0.72 because this is actually something that came out of the previous iteration. This then lets me end up in 0.43. Okay, and this I can do for the whole state space as well. These things will still be 0 in here because there is nothing else initialized in here yet. But I can actually iterate this through, and after 10 iterations, I will already have this estimation, which in fact is not the optimal value function yet, but the greedy policy that through the argmax operator that I would actually extract from this is already the optimal one, because if you see in here, so these arrows actually are the argmax operators that actually calculate the value I can expect going there with the noise and the expected value of the next successive states. And this is actually already the optimal policy that I can take. Also see that if you would start in here, then you would also go here and up and there. So, and you see that the values between iteration 10 and iteration 100 do not change so much. Policy were already stable. Values will update a little bit, but at some point they will go below some threshold and you will stop, and then you can just, through the argmax operator, extract your optimal policy. As a side note, you can of course do this with the so with the state action value function as well. So this was the Bellman optimality equation operator that we defined in the previous video. So you can also use the same one for the Q function, and then you can calculate for each state and action pair the optimal Q function, which is something like giving you a one-step look ahead at this point. So you can just, in this case, if you want to have the argmax operator for extracting your optimal policy, you do not need to take the probability for the transition in the next state into account. You can just select the value actually in this state that is actually the maximum, and this is something that you would then take. So in this case, it's always what's really whitish in here. This is the highest Q value, and this is the Q value that you would take. Okay. Now let's play around with our parameters a little bit. Now imagine that we had a discount factor of 0.9 in the beginning. So the value of the successor state is only counted with a decay with a discount of 0.9 into the state value estimation of your current state. Now imagine that what would happen if the discount factor is not 0.9 but it's still 1. So it doesn't discount any state values for future. So it doesn't discount any future returns that you could expect. Maybe think about it a little bit. Okay, so what would actually happen? You wouldn't decay any state values of successor states, meaning that if you are in this state and you select action right, there is no decay in saying that the next successor state would give you a return of 1, and you would just take the max operator over this equation part of your action selection. It will not be decayed, so the value that you expect from here is also 1. And this also goes through your whole state space. There will no decay of any state value, so this will propagate through all the way through your available state space. Yeah. Now here the problem is what you now see in here. What's really interesting is this is a little bit different in consideration to the beginning, because if you actually put the discount factor of 1 in here, so will not discount anything, the best thing that you can actually do in this state is going left. Because going left in this state is the only way that you will not by chance end up in this one. So taking or selecting the action going left in here either takes you to the state above, to the state below, or remains in the state in the same state, meaning that this is the only action that actually gives you a 1 value for this state. So this is maybe a nice example why a discount factor of 1 is not always the best thing that you can do, because this would actually be not the best policy or the best way of acting that you could achieve, or that from the application point of view. The same happens, of course, in here. So even though you mean going left is best at this point, with a discount factor of 1, the best thing that you can do in here is going down, because this either takes you to the right, so leaving in here, going down, so also leaving in here, or by chance going to the left. And this is also something, some artifact of that. And if you see this in here, so also from here, you would imagine that going up is the best thing that you can do, because it's the quickest thing. However, going from here to up all up there is a chance of actually ending up in the red area in here, which is not something that you want to have, that the algorithm with this configuration want to have. So it will always go around this one, taking the long term to the goal, because then noise will not integrate anything. So, okay, if we have still the gamma of 0, so we still do not discount any values, what if we remove the noise? Well, then, if we remove the noise, then everything is fine again, because there is not any chance that we will end up in the -1 in here. Meaning that, albeit everything is, all state values are 1, we will still have the best policy to actually get. So this thing in here could also be numerical issues then, because everything is equally likely. So we will have a problem in here, because actually there's also an animation on that. So the thing is, without the noise, you will actually end up, you can work with a gamma of 1, but however, you will stuck in infinite loops in here. Because actually, if you calculate the state value and you are in this state and you go up, the state will still remain 1. So you actually have this infinite loop problem, which we also discussed in the first lecture. So also no nice configuration to actually configure your MDP. And now a little bit more realistic scenario. What if we have a one-step transition reward of minus 0.1, which is basically meaning that for each step we take in our MDP, we get a punishment. This is something that you will find a lot more often in practice, because you want to incentivize the agent a little bit in going to the goal as quickly as possible. So you do not want to end up your agent like going infinite loops in your MDP. You want it to go fast from the start to the end. And this is what your values for that would then look like. So now so now you would really have a policy that in this case from here goes all the way up and the right, but also that from here would go here and up, so would really take the direct way to the goal. So this is a configuration that you would really select in practice, and this is an MDP configuration that you should also consider for yourself if you're implementing things. Okay, one thing maybe to mention is exactly this point. So if the reward for the one-step transitions at this point would really decrease to like something to 0 but a little bit below, you would see a change in this selection here. This configuration was really nicely because with the noise and with the one-step reward punishment in here, you will still favor the agent to go up in here. But if you play around with the values a little bit, so if you're implementing this on your own, which you will in some format do in the exercises, and if you want to play with the values, we will see certain configurations or results where the policy in this case will not go up but still go to the left side, depending on the one-step cost for transitioning through the environment compared to the noise, which may end up the agent in the negative reward side. So here you can play around with the cost of one-step returns over the risk of falling in the trap in here. This is something very intuitive to understand if you play around with this a little bit. And of course, in the same case, you can also do this directly with the queue function. Okay, another example to give you some intuition now, not like with certain values explained, but this is a nice example that's also very commonly used in practice to actually tell you the thing behind risk and getting a conservative agent versus getting an agent that is really keen on getting the most reward from this from the MDP. So in this example, just assume that there's a start state. And there is two terminal states actually. One is this one and this is the other one. And the first terminal state gives you a +1 reward and the second terminal state gives you a +10 reward. And there is a cliff in here. So if you end up in here, you get a -10 and the episode ends. So the question now is, how do environment noise and discount factor actually affect your value function and resulting policy? So if you assume that the discount factor is 0.1, so we discount future returns harshly, so very, very hard. We will discount them a lot. There is no noise. What behavior do we expect? Actually, the behavior we would expect is that the agent prefers to go to the near exit. This is this one, because the additional steps that the agent would require to go to the distant exit would not pay off actually. So although the distant exit, the reward of the distant exit is 10 times larger than the reward of the close exit, however, it takes me at least 3 more steps. Basically, this diminishes actually the additional reward I can actually get from the distant exit, because I actually punish it and decay it by 0.001. Okay, why is this the case? The gamma factor forces the early termination, and as the noise is 0, there is actually also no risk falling down the cliff. So we will just go all the way along the cliff and then prefer the close exit. What if we change this a little bit? So discount factor is still 0.1, but the noise is 0.5. So there's a large chance that I will not end up in the actual state that I want to go to, depending on my actions. In this case, because of the gamma factor of 0.1, we will still prefer the first exit because the additional reward for the distant exit doesn't pay off. But the really important thing is the agent really tries not to go along the cliff because the chance is far too high falling over. It will immediately go up and take the upper row actually to go to the near exit. And another example is, what if we would not discount the future reward so much? So there's a discount, but it's very low, and there's no noise. So in this case, of course, there is no risk of falling over the cliff, so we can easily go alongside the cliff. And now, in fact, it's for the agent, it's better to actually prefer going to the distant exit, because with the discount factor that is nearly 1, there's almost no discount on the reward. So it's actually much better to go for the 10 reward instead of the 1 reward. So we actually allow the agent to go to the distant exit. What if we add noise on top of it? Then of course we see something similar. So we will still go preferring to the distant exit, but we will go the upper road actually because we want to be safe and not falling over the cliff because of all the noise. Okay, so if you want to play around a little bit with it, so we will implement it in the exercises, but however there's also a nice example or nice JavaScript applet by Andrej Karpathy that you will see in here. You can just select, so this is like a similar grid world that you can select, that you can also configure if you want. So you can just select cells and then you can also add some reward in it. And what you see is that you can just, in here, where is it? You can run value iteration. If you just put on this one, if you just push this button, you can run value iteration. For your MDP, there is not much cells that actually give you a reward. You see it in here. So this cell gives you a +1 reward, this cell gives you a ± reward, and so on. So there's a few cells giving you a reward. And you see that if I'm resetting it and then toggle value iteration, then you can see all these sweeps through the environment, and you see the values that you actually calculate. And depending on this, also the argmax policy that is actually extracted from it. So the link is provided on the slides, and just I encourage you to play around with it to get some intuition about how value iteration actually works on such simplistic grid world examples.